Today we're going to talk about rate, time, distance problems, which tend to be pretty tricky. So we're going to start basic with some general principles and then move to more specific applications and problems. So here's the big idea. If I want to go to the Cape or someplace that's 120 miles away, and if I'm driving 30 miles every hour, how long will it take me to get the 120 miles? Well, of course, it's going to take me 4 hours because 30 miles every hour times 4 hours will equal 120 miles. And by the way, in science, you can see that the units cancel out as well, showing that I have 120 miles. 30 miles every hour for 4 hours gives me 120 miles. If I, on the other hand, am driving 60 miles per hour, and I want to go that same distance, how long will that take me? 60 miles every hour means that that's going to take me 2 hours. These are some really common sense applications of a basic idea that's at the heart of all these problems, and that is that rate times time equals distance. So if I take that basic idea, if I know that if I'm traveling 30 miles or 30 miles per hour, and I don't know how long I'm traveling, 30 miles an hour, I know that rate times time equals distance. So even though I don't know exactly what my distance is, I know for a fact that it is 30 times x, because rate times time will always give me my distance. So I might not know my exact distance, but I have a variable expression for it. Or maybe this is probably more likely to be kilometers per hour. Anyway, it's going to be 30x. Remember, 30 miles an hour times 4 hours gave me 120. Because I'm involving variables here doesn't take away the truth of that basic fact. Some other things I want to point out in this, if I were talking about 30 kilometers per hour, if my rate is in terms of hours, my time also has to be in terms of hours. So that can be kind of tricky. If I say I'm traveling for 15 minutes, how many hours is that? Well, fractions are part-to-whole ratios. So if the part is 15 minutes, the whole hour is 60 minutes. So I can always change my minutes into fractions of an hour by putting the minute over the whole hour, which is 60. Some other tricky things to remember are that whenever I have the variable in time, I'm going to want to think, are the things leaving the same time or not? Actually, let's go back to that later in a different problem. Let's talk now about the way we set up our charts. The good thing about all of these problems is that the charts are always the same. So we're going to do rate times time. This is what we've discovered is the universal truth, is always going to equal distance. And in most of these things, we're going to have two different categories, and we will fill them in. I don't know, you'll be the first plane, like a plane or a jet might be what's being compared. That all depends on the words of the problem. That's not what I'm trying to get at. What I'm trying to get at is that just like always in these chart problems, you're looking to fill in these 4 categories first. and the variable can only go in one of them. Okay, so you're going to fill in these 4 boxes with the facts of the problem, and then you will multiply across to get an expression, a variable expression for distance. At which point you'll look at the problem, look back at the problem, and see how can I use those to make an equation. So let's see our first type of problem. Here's our second problem. It's a little bit too big, but I'm going to try to do the basic chart above it. So, Carla begins biking south at 20 kilometers per hour at noon. Dean leaves from the same point 15 minutes later to catch up with her. If Dean bikes at 24 kilometers per hour, how long will it take him to catch up with Carla? Well, you might be panicking right now, but always start with what you know. Rate times time is going to equal distance. And we've got Carla, and we have Dean. And I think, whenever you feel overwhelmed, you want to start with the easy stuff. And you can see that Carla is biking at 20 kilometers per hour, so clearly her rate is 20. And Dean is biking at 24 kilometers per hour, so he is 24. Now our variable is in the time category. And the thing you always want to ask yourself when it's in the time category is, do they leave at the same time? Always. That's your question. Because if yes, then the variables are the same. If yes, both are t, or x. If no, let's look at a little simulation here. I've got 2 people at the bottom of my screen, supposedly, and they're going to go, both of them are going to start here and go up to here. Okay, I'm going to erase this to make it look better. Okay, so here's my simulation. The one on the right starts out, it's going kind of slow, and then the one on the left, oh, come on, draw. Okay, the one on the left speeds up. Okay, I'm having stylus problems. But the bottom line is, I really do have to be able to show you this, so I'm going to try again. Here we go. Here's stylus 1, stylus 2. They're both trying to get to this spot. Can I make them both draw? Okay, so this one on the right leaves. On the right leaves, and it's going along, and then the left one. Okay, it's really not working. I'm sorry. What I'm trying to show you is that the one who leaves early is going slower. The one who leaves later is going faster. To get to the same point, the one who leaves later is less time. Think of that, later. L is less time. So if Carla leaves at T, then Dean leaves 15 minutes later. Well, remember, we are talking about kilometers per hour, so we need to express 15 as a fraction of an hour. So it's going to be T minus, because later is less, 15 sixtieths, which is the same as, because that's the part to whole fraction, if I'm going to simplify that as T minus 1/4. Later is less. The one leaving later is going faster. So they're spending less time traveling. Multiplying across, I don't know how far Carla got, but I do have a variable expression for it, 20t. I don't know how far Dean got, but I have a variable expression for it, 24 times t minus 4. Now I'm ready to think about my equations. Let's look at the problem. They're starting from the same point, and he's going to catch up with her. So let's take a look at what that looks like. So let's take a look at what that looks like. We know that Carla starts and Dean are starting at the same point. Carla leaves and begins her trip. Dean leaves later, but in the end, they get to the same spot because he's going to overtake her. Okay? We don't know what either of these distances are, but we know that Carla has a distance of 20t. And we know that Dean has a distance of 20. We know that Dean has a distance of 24 times t minus 1/4. Looking at these two distances, I can see that they are the same. And therefore, what I have to do, looking at their distances and making an equation, I have to decide how they relate. And if she's starting in the one place and finishing in that, and he's starting in the same place and finishing at the same other place, then their distances are the same. And in math, the same means equal to. Now, sometimes kids have more problems with the fractions than anything else. So 20t equals 24 times t is clearly 24t. And then 24 times 1/4 is like saying a fourth of 24. So that's minus 6. When I do this, I've got negative 4t equals negative 6. So that equals 3 over 2. 3 over 2 is 1.5. In our chart, we said that Carla's time was going to be t. So that means Carla is traveling for 1.5 hours. But the question asks, how long will it take Dean? So Dean is 1.5, which is an hour and a half, minus 15 minutes. An hour and a half is 90 minutes. Minus 15 minutes is 75 minutes, or 1 1/4 hours. Don't worry too much about those last-minute computations with the fractions and answering the questions. For now, I'm much more interested that you can understand how to set up the chart and hopefully get an equation. We can work on the fine points after this. Here's our final type of problem. A ski lift carried Maria up a slope at the rate of 6 kilometers per hour, and she skied back down parallel to the lift at 34 kilometers per hour. The round trip took 30 minutes. How far did she ski and for how long? Okay, again, it seems overwhelming. So we begin with what we know. Rate times time equals distance. Our two categories are up the mountain and down the mountain. And so let's talk about what we can see. What do we know? Well, we know her rate up the mountain is 6 kilometers per hour. We know her rate down the mountain is 34 kilometers per hour. That means the variable is in t with time. Okay, going back to something we learned. All we know about time is that it took a total of 30 minutes. So if you remember, what happens when all we know is that two things add up to it. First of all, remember, it's hours. So 30 minutes equals 1/2 hour. So if I know the whole thing is 1/2 an hour, if I call one of them t, the other one is 1/2 minus t. Because 34 is a bigger number, I want to use the easier variable with it. And this other one will be 1/2 minus t. The rest of the time from the 30 minutes total, if this is part of it, the rest is the total, half an hour, minus this part that we've already designated. So I don't know what any of this is, but I do know that 6 times rate times time will give her distance up, and that rate times time will then give her distance down. This one's pretty easy to understand because she's going to go up the mountain and down the same mountain, parallel to. That's why they use those words. So clearly, these two distances are the same. So 6 times 1/2 minus t is equal to 34t. That means that 3 minus 6t, because half of 6 is 3, and 6t equals 34t, which means I'm going to add 6t to both sides. And that gives me 3 equaling 40t. So her time is 3/40ths of an hour. Again, this can get pretty tricky. So you really want to know what her total time is. So it's 3/40ths of an hour, and you could say 3/40ths is how many out of 60? And do it like that. So we've got 180 divided by 40 is equal to 4.5. 4.5 is the amount of time she spends. And now this is minutes, okay? Oh no, actually it's not. Her time is 4.5 minutes. Yes, it is minutes. And times 34. What they want to know, the problem is asked for how far did she ski? So that means we're talking about distance, and this is the distance that she skied. So you have to say 34 times the amount of time, and 4.5 times 34 is, oh, okay, well that's 153 minutes. Actually, let's go back and okay. It is 4.5 minutes, but if we want to then multiply it by 34, we need to do, this is 34 kilometers per hour. So what we actually need to do is this number. This is how many hours. I was going to minutes, but since they want the distance, we have to go back to saying times 34. And we get this whole big, long thing. It's 2.55. But let's not worry too much about that. The whole idea is to set up the equations in the way that involves the chart. I'm not so much worried about all the final minutia at the end. If you understand that those two distances equal each other, that we had 6 times 1/2 minus t equaling 34t. So 3 minus 6t equals 34t. Adding 6t. 3 equals 40t. Time is 3/40, which, as we said, is in fact 4.5 minutes. But I'm not going to ask you anything complicated with ridiculous decimals or anything like that. So you just need to know how to set up the charts, how to get your equations, looking at them, and then solve to the best of your ability. If your answers don't match exactly what you find in the back of the book, go back and make sure that you've answered the question that the problem is looking for. Sometimes it will ask you, what time did they get there? If we go back to our problem with about Dean and Carla, we saw that it would take Dean 1¼ hours. So what time would that be? If they started at noon, and it takes 1¼ hour, then that means that it's at 1:15. So sometimes the times are not clear. But in general, just remember that what you do is fill out the chart, the 4 boxes of the chart. Two, find variable expressions. And then look back at the problem to see how to make an equation. In general, the distances either add up to a third number like if you have them coming toward each other. Remember that one with his 60, so this distance and this distance added up to 60. Or if we started in the middle and they went in the other direction, they would still add up to 60. Or else, if you have somebody starting out and then somebody catching up, then the distances are equal to each other. As far as all the complicated times and all that kind of thing, don't worry about that. But do express time in terms of hours. So good luck, and I'm sorry for the confusion at the end of the third example, but I think the basic idea is clear there, that if you're doing round trip, the two distances equal each other, and you get your basic answer. Don't worry too much about the interpretation after that. Good luck, and whatever you do, do not panic. We will be going over these, and it's going to all work out just fine.